So, this is now lecture 9 on model suites. That is a pre-last lecture of the second part of this module. In the previous lecture we have been tackling conceptualization and conceptual models. And now we have been tackling quite a good number of topics, models are everywhere, case studies, a notion of model, languages and models, systematizing and summarizing somehow elements of models, deep and normal models, conceptualization and conceptual models. Now we will go to model suites. It is our belief that typically we are using not only one singleton model, but we use a number of models somehow at the same time, in parallel, and having the same, let's say, issue in mind, maybe the same set of origins, maybe a number of origins that we have to consider, and we need to have some kind of control how to handle such kind of model ensembles. In the sequel we will call these model ensembles model suite. So we come to the notion of the model suite. We consider horizontal and vertical model suites. We consider composition to model suites, model capsules as a trick to handle model suites, collaboration and association, and finally we turn to a case study to show how it works, at least in computer science. Okay, model suites should help us to understand the large variety of models that we have in mind. Of course, also somehow try to help us for theory development, and we have a good number of thoughts, culture of life, of all aspects we have been already considering in the fifth part of this lecture. Let's consider a very classical computer science example. We think about, let's say, qualitative models. We have a number of qualitative concepts, a qualitative theory, and what we want to have is, of course, somehow a support by data, by quantitative. That means, in this case, by quantitative reasoning or theory development, or let's say based on a number of quantitative concepts. In this case, we might have something like genodata. Here we have, however, our knowledge, our theories, our skills. That means we have two different things in mind at the same time, and the model is used, as we do it quite often in computer science, as a mediator between quantitative and qualitative reasoning. Additionally, we might consider models at a variety of levels. We might have micro models, like we do for operational models. We might have shadows that are our perceptions. We might have meso models that are maybe our tactical models, and we have macro models that somehow represent systems at a strategic level. And we might have been using it for system composition, for operationalization, for abstraction, for semiotics based on science, whatever is useful in this case. That means in this case, typically we go with having many models. We start with an origin, and then we represent some properties of the origins that are of interest. That means that are within our focus, that we should represent, that are useful, so that the model can really represent the origin in the given scenario as an instrument. And then we have some kind of objectives, and then we model it by in very different ways. For instance, we have a construction scenario, we have a communication scenario, we have a documentation scenario, we have an analysis scenario. We have, however, a requirement. The model suite or the model ensemble should be coherent. We might also have maybe in a good case the same objectives, the same properties we want to represent, and then we might use such kind of a model ensemble or model suite for understanding, for optimizing, for managing, for simulating. What we do in all these cases, we use some kind of binding procedure, and then we develop a number of contracts so that the models are properly bound to each other, and we can use those contracts as a basis for constraints, for having some kind of facility to maintain the model coherence. Another problem with our model treatment is that models evolve over time. And evolving over time means in this case we have to have a facility to handle pre-models or models that we have been previously using by maybe our models at present, and also have maybe a glimpse of an understanding how the model is going to be used in future. That means in all these we have now multi-model environments. That means in this case we need some kind of explicit specification. We need to integrate somehow the different models. We should be able to co-evolve the models if we separate concerns so much. We should be also able to combine different representations, maybe even by very different kinds of models. And of course our evolution should be somehow supported for our models that we develop over time. That means in this case we need the management of multi-model information systems development, or multi-model systems development, or multi-model development in general. We need, for this reason, also some kind of version handling, and we need to have some kind of glimpse at least, or understanding what means refinement and what means abstraction. For this reason we come down now with the notion of a model suite. So we can live in a model with a model and ensemble, and we have a sophisticated and maintainable association. That means we target at a systematic, multifaceted modeling approach. Okay, what is now a model suite? We can say a model suite is nothing else as a collection of models, or a set in the best case. As a second property, we have to use some kind of association or collaboration schema among the models. That means in this case we are using a direct binding procedure so that we can have really properly represented our contracts. If we use such kind of associations, then we need controllers. So in this case we are able to maintain consistency or coherence of a model suite. And that means we need in this case also some kind of application schema for explicit maintenance and evolution of the model suite. And it would be also nice to have some kind of tracers that allows us to establish the coherence in a proper form. For this reason we should have some kind of specific treatment of coherence. One bad message is, however, that we can use it only for incrementally or inductively defined languages as some kind of pretty nice support for the compositionality principle. That means in this case we have to concentrate already. And if concentrating, then in this case we should also concentrate on models representing discrete domains. So a model suite is nothing else as a set of models that is defined by usage of some languages. A language has typically, if we start with a mathematical logics approach, a signature, and based on this signature we define constructors so that we can have well-formed expressions in the language. Then we can say, okay, fine, now I restrict my consideration of expressions in the language to specific model types. That means we have a language of the model and we have constraints for somehow handling statements or expressions given in this language so that we can have some kind of well-formedness by these constraints. And then we might associate our models by partial mappings of the languages. That would be the best and nicest case. And a model is nothing else, let's say, as some kind of structural expression in these languages that of course obey our constraints. And we might have additional, maybe model constraints defined in the logics of this kind of language approach. That means in this case, the model now, or the models in the model suite, is bound by some model association that represents in reality the contracts among the models. So we have to have some kind of explicit association among the models. It could be based on the classical collaboration 3C paradigm, so that we have some kind of exchange, maybe we call it communication, some kind of coordination among the models, and some kind of own story of each of the models. And then we can say, okay, fine, we have an association style. So it could be, in computer science understanding, some kind of supporting program set, or it could be even data access pattern. At least the association style is somehow based on some kind of style, of some kind of workflows, how we can use it in a proper form. So in this case, we should maybe consider a number of different patterns for such kind of associations. So a model suite now is defined as we have a number of models that are somehow bound. So it means we can say, okay, fine, in this case we can introduce an abstract model suite type that says, okay, fine, what kind of models we are using from which languages. And additionally, we have binding constraints. So in this case, these binding constraints represent our associations. And then we can say a model suite is nothing else as something that is defined on a model suite type and set or base, of course, our integrity constraints. So in this case, we can say now our contract consists now of those integrity constraints given by the languages and of those that bind the models in a model suite together. That means in this case the contract should also contain some kind of enforcement mechanism that allows us to somehow to handle a change of a model within a model suite so that it is really still coherent with the other models in that model suite. That means we need to have some kind of enforcement mechanism and a set of maybe evolution transformations that allows us to handle somehow changes, development, and maybe also different maybe replacements, migration of models within a model suite. That is nothing else as we have now, let's say, a model that is somehow bound to another model, Mi to Mj. We might use a general pattern for this. We say, fine, we extract a part of this model Mi in such a way that this can be somehow mapped later to a part of a model from Mj. So we extract some parts, we transform this extracted submodel and load it to our model Mj. And in this case, you can say, okay, fine, we have maybe some binding and transforming facility going back. That means we have a model I and we have a model J. And in this case, we have some kind of coordination that says how these models can be bound to each other. The problem, of course, typically is that when we map a submodel to another submodel in the other model, then the submodel that is going now to be mapped back to the first submodel is, of course, maybe different from the submodels that we have been using for mapping to the right side. That means in this case we have now to handle somehow some kind of category setting in order to handle this explicit mapping among models. Okay, fine. That means in this case our task is now to develop a number of binding mechanisms for integration, for calibration of models, for structuring and functional integration especially. And coordination is something like our maintenance facility for handling coherence, consistency in our model suite. Of course, in this case, each model in the model suite obtains some obligations, some permissions, and of course is also restricting changes to itself by other models so it is has some kind of protection mechanism. And then in this case, we can say, okay, fine, we have some kind of evolution choreography, some kind of configuration support, some kind of versioning support, some kind of orchestration support in order to handle co-evolution of models within a model suite. That is now the general, let's say, setting. How it is done a little bit more concrete. Okay, in this case we say, okay, fine, we go with maybe different binding forms. We have an eager or an explicit binding for models in the model suite. And then we use some kind of sub-modeling facilities. That means we have for each of the models some kind of import and export interfaces. And we can use a pretty old approach that is called infone, that is containing the content, our submodel, the association we have been somehow using, and maybe a little bit of characterization like in an informative model for the competence. And then we can say, okay, fine, the association characteristics are specifying now which model is now in which way dependent on the other model. I think we shall somehow discuss it for the special case of information systems in a minute. And then we can say, okay, fine, then we have also a qualitative association. The qualitative association could be that the model suite is consistent. In most cases we don't need consistence, we need only coherence, and for this reason we have maybe some properties that should be true. And then in this case we can say, okay, fine, if we associate, we have some kind of exchange frame that is based on the architecture, on the conceptual model of the model suite. And that means in this case we have maybe also some kind of association style, some association pattern, so that we can handle this kind of association among the models. Okay, that means in this case we have now nothing else as we have a model consisting of its own model and consisting of some kind of exchange submodel. And of course, let's say we have, some complex operator to somehow to handle composition of models by their own part and by their exchange part. And the same would be, let's say, also for the other model. Then in this case, you can say, okay, fine, we have now a complex association schema, so that we can construct our model MJ based on the exchange. That means we have again this extract, transform, load pattern to associate models. And we say, okay, fine. In this case, we can have now some kind of coexistence constraint. The coexistence constraint says, if we map MI to MJ, then of course it should be a sub-model by this extract, transform, and load facility. And we should have also another mapping from MJ to MI, so that it is again a submodel of that model. Maybe with a restriction to the submodels that would ease the task of specification, but in general we would have some kind of model change propagation in a model suite. We can handle it, and I will show it on a pretty nice example. Let's say we have something like a specification of a database system, given a signature, given a language, given a schema notion, giving some kind of content in our database, and then we have the content objects. We can have another, let's say, database, and we might have now some kind of mapping in the category of signature, or we might have a language mapping, or we might have a compiled schema mapping so that we can transform the schema 1 to the schema 2. We might have also a facility to reason on that. That means we have some kind of observations, and then we can say, okay, fine, we can have it also on the databases. The problem with the databases, of course, is that we have to have a pretty sophisticated ETL infomorphism. The notion of an infomorphism I have been already introducing in the case studies lecture. Then you can say, okay, fine, I have now my algebra, so I can now map my objects to some set of objects in the other way. So we can say, okay, fine, we can also now think about some kind of revised, evolved signature. evolved language, evolved schema, evolved content base for our database. So it would mean in this case we have some kind of mappings between one model world to the other model world. This has already been done in our web business specification. For instance, you have something like an abstract state machine specification, and you want to have some kind of transformation to a BPMN or to XPDL or to BPL. Then in this case you use this mechanism, and then you can say, okay, fine, we have maybe some kind of revised BPMN as a final result. The same you can do also, let's say, if you have something like a relational database platform, and here you are mapping to an XML oriented database platform. That means in this case you have again this kind of association among models. The good thing is the theory of institutions has been developed in category theory and can be now used as a general setting for meta logics among models. Okay, I think we don't need to consider all possible ways how to associate models in a model suite. Let's consider two very specific and nice cases: horizontal model suites and vertical model suites. They are mainly on different abstraction layers, they are mainly aspect oriented and represent somehow some kind of different concerns. Let's say a model suite can be in a low-class design setting, something like you have a new UML approach. You somehow transfer this UML approach now to Java programs. Or maybe you have the co-design approach, that you map whatever you have been developing, let's say for the storyboard, to a number of database programs. That means in this case, you can map in a localized design setting the schema of one approach to the schema of another approach. The same happens if you go for the globalized design setting. As already considered, in the globalized design setting, we consider a schema as the main source, as a global schema, and we add to the schema some kind of viewpoint schemata so that we can have as derivatives of the global schema a consistent model for, or coherent model for our origins that are our business cases for information systems, for instance. Another way is vertical model suites. In this case, we use different abstraction layers. Horizontal model suites have been using the same abstraction level. And now we can say, okay, fine. A vertical could be, for instance, that you have some kind of model that represents the micro data, that represents somehow the compiled, let's say, matured data, or that to another schema that represents maybe our analysis data. So in this case, you have some kind of layering among the models in the model suite. A similar layering you can observe, for instance, for the M0, M1, M2, M3 meta representation, how we do it with some meta approach in modeling. Or you can say, okay, fine, a stratified model suite is based on a composition architecture. That sounds a little bit very general. Let's consider a more specific case. Let's go first to hierarchically layered model suites. In this case, we can say, okay, fine, I have my micro database. That could be, for instance, all data for, let's say, train connections in an area, all data for passenger movements in an area, and all this is represented in the micro database system. So in this case, you say, fine, I'm interested only in a part that can be analyzed. It means I build an auxiliary database and use this auxiliary database in order to have some kind of meso database system. So I can store it, I can capture it, I can have some kind of analysis facility for, let's say, going over the snapshots in the database. And then I can say, okay, fine. This database can be used as an analysis database management system. And in this case, maybe I'm again injecting some auxiliary data And then again, I have now my inserted data that are either modifiable or that are injected directly to the other part. And I can go now, let's say, for some kind of presentation database management system or database system. So in this case, you have now 4 different models representing the micro level, representing the meso level, representing the analysis level, and representing the presentation level of data in my database. That means I'm using 4 horizontally layered, in this case under the same paradigm and platform, models. Okay, in this case you can say, okay, fine, data that are injected and not modifiable are injected again, are injected here again, and for this reason I have now a facility. I don't change data on this line, and I might change data on this line. That means in this case I have now some kind of explicit ownership, some kind of explicit explanation how the data are associated to each other. And I can directly handle it, of course, by a model association. And if I'm using the same platform, that means I can use the same language. That means I can use some kind of similarity in my signature. And for this reason, the mapping problem is a bit easier. That is hierarchical layering in model suites. The vertical layered model suite is very commonly used in communication systems architectures. You have something like communication on level I, and you go to communication on level I+1. That means in this case you have this kind of communication architecture, and you can say, okay, fine, all data are somehow used from layer I to layer I+1 by some kind of data transformation facilities, and you can accept the data building this way. Another vertically layered model suite is typically used in complex genotype or genodata and phenotype data considerations, like you use it for the human heart modeling, where you reason on the protein level before you reason on the gene level, you reason on, let's say, the cell level, you reason on the tissue level, and you reason on the functionality level. That means in this case we are changing even the abstraction layers and the languages quite heavily. What is one also? Okay, fine. Now we have maybe for the horizontal model suite, we have mainly models at the same abstraction level on layer, and we have here, of course, also in the vertical model suite maybe some kind of meta model for associating models in a model suite. One is the master slave, another one is the stratification we have been considering already. This is wrong direction. Okay, so it means in this case we have now model suites that are using maybe some kind of concept space, like we do in conceptual modeling, some data space, maybe also some consideration or hypothesis space, and of course, since we are using models as an instrument, some target and goal space. That means in this case we have now very different dimensions to consider, and in this case our model suite maybe is already given by this kind of aspect or facet separation of concern. The same we have, let's say, for streaming, microdata, metadata, and macrodata, as we are using in streaming applications. We have some data, we have some context, we have some quality data, we have some docket data, we have some restrictions for access, maybe we have some security profiles. In this case, we have again the same approach based on some kind of data stream profile in this case. That means in this case maybe we can use for composition something like a layering of, let's say, coherence within a model suite. The same happens if we use some kind of OLDP, data warehouse and data marts approach. We have the OLDP schema, we can now have some kind of extraction schemas, and we can build our OLDP data warehouse representation. We can build a cube schema, and then we maybe have some OLAP schemata. The same we have, however, also in classical information systems modeling. We have typically a number of models that are used, let's say, in somehow coherent manner. And maybe we can learn from this approach a lot. We use here, first of all, a data structure model. That is consisting of the database schema with all its specifics, that uses all the static and technical constraints. And then we say, okay, fine, a second model is the database function model. It provides the database functionality and, of course, a set of dynamic and technical constraints we might use. We have also, let's say, a database support model for the content we want to represent or for the interaction we want to support. And now we have a funny thing. We start typically with a structure model. In database applications, we think that for this reason we can have directly associated and somehow as an slaved model the content model. The content model can be used because of our functionality is given typically in this kind of generic approach. For the interaction models, is that what we are using, for instance, for our menus, for our displays, for our, let's say, web interfaces with our database or information system model. And then in this case we can say, okay, fine, if we have the idea to change the content, then of course it pulls back to a change in the structure. It pulls also back to a change in the functionality we have to use. This functionality now, however, pulls also back to the structure and at the same time also to the content. That means in this case we have with this change a little association of changes within a model suite. Additionally, of course, a change in the content changes also some kind of representation. So that means we have to change the representation model. Going this path again, then in this case we have also a second change in the action model. That means in this case we can say, okay, fine, something is somehow the ruling part. It governs the content model. It governs the content model governs again the interaction model. Given this kind of generic functionality for our database management systems, we can say, okay, fine, in this case we can have this kind of database function model directly associated with the database structure model. This is the driver and this is a slave. That means you have here a master-slave model connection. In the same way we can consider the content model or the interaction model in a slave dependence on the database structure and on the database function model. Maybe in this case we can handle somehow this co-evolution, how we do it typically in well-designed database applications. Okay, that means we come now to the composition of models. We can construct systems this way. It is not a universal approach. We will never have a universal approach to all kinds of models, but it is for systems realization and systems construction maybe a very good approach. In this case, you can also say, okay, fine, when we need later to inject a new model or a new component, then in this case we have to can handle it through the model suite itself. That means in this case we can say, okay, fine, we go now for model suite composition with the abstract strategic concern. Then we look how we can develop it based on our methods and our molds and our strategies. Then we can go with our frames we can use if we have some kind of generics in the background, mainly related to the tactics. And then we can say, okay, fine, then we can master and design, and this is nothing else as the adaptation and using all the techniques, and finally we can deliver it. That means in this case we could use such kind of strategic, tactics, operational approach to the model development and the model suite composition, starting maybe with the landscape and ending up with the finally realized system. In this case we can have a number of association patterns. I would call them association meta models. We have maybe a proxy association. In this case we use partial copies as proxies, and we somehow deliver it to the other partner. Or we have a broker association. That means in this case coordination of communication is either directly or through message passing or something like that. A very sophisticated and nice way is to have this kind of master-slave association. That means in this case we use directly one master model as the governor and the rest of the models are somehow slaved. We might have a client dispatcher association or a publisher subscriber association. One very nice pattern is also the model view controller association. That means in this case we have a model that allows us to have different views, and the controller selects the most appropriate view that we have to use in this case. That means in this case model association can be also somehow patternized or stereotyped, and in this case we can have a pretty nice construction model for our model suite. In this case, we can say, okay, fine, we can build coordination contracts. Which kind of contract between party, appropriator, and the possessor, and the trustee, and an arbitrary are 4 different roles a model can play in this model suite. And we have some kind of exchange, some kind of monitoring, since we want to have our tracers and controllers, and of course some kind of enforcement procedure. That means in this case we can use the classical way how we are handling all this kind of coordination in a collaboration system or collaborating system in the same way. We can say, okay, fine, if we use the coordination specification, then in this case we can say, okay, then this is generally based on a contract that can be changed over lifespan, and of course we might have variance between the parties, organizations, and the infrastructure that we can use in this case. A similar way could be also for the submodel characterization. So we say, okay, fine, we have some kind of characteristics. We say now the party is nothing else as a submodel, and it plays a certain part in a certain organization, uses a certain infrastructure, and then we can say, okay, fine, our submodel has a certain submodel profile, maybe some kind of demand of injection of parts and pieces. That means in this case we have now a general way how to associate models in a model suite so that it can be handled in an appropriate form by enforcing mechanisms, and we have in this case tracers and controllers. That means in this case we have some supporting programs, we have some kind of model access pattern, some kind of model association, some association interplay among the models, the same as we do in classical distributed database systems. And we can use this kind of association pattern to specify how the association among models is done in the model suite. We might also somehow support a number of principles. I consider here maybe a small number of principles we can learn from object-oriented approaches, or let's say from very good other programming approaches. They have the downward dependency principle that says, okay, fine, the main data structure is top-down. We have an upward notification principle that says if we have to make some change that may have an impact on the more global models, and in this case, of course, we have to report it somehow. We have also a neighbor communication principle, so that we can say, okay, fine, my neighbor model must know what kind of changes I have been making. We have, in this case, explicit associations. We might consider only modeling approaches that don't allow cycles among the models, especially cycles among the enforcement mechanism. And maybe we have a good naming principle for the layers among these models. We might have now a number of requirements for model suite handling: explicit specification, integrated development of different models, co-evolution of models, combining different representation with mathematical rigor of models. That is one of the very difficult matters, but if we do it so, then we have, of course, a very good way how to develop it in a proper form. And we might have evolution of different representations, management of model suites, and maybe also version handling in a proper form. Explicit specification of model suite association means the interdependencies among models must be given in an explicit form, and the deep models are known or already combinable in a proper form. The consistency of models, in this case, it must be somehow recursive or incremental. Integrated development of different models means that the models are used to specify different views of the same problem or application. That means in this case we have some kind of consistent usage, and the integration must be made explicit. That is pretty difficult. Coevolution means in this case the model suite must allow data elements or elements exchange between the models. Combining different representations is of course a matter of developing a good mapping. That is not a matter of analogy only, that is a matter of mapping. Evolution of different representations, of course, is a very difficult matter, because if we have now the association among the models, and a model can also evolve somehow. Now it seems that it is almost impossible, but I will show in the sequel that it is easily possible to handle it somehow. Okay, before coming to this, I would like to introduce another concept that is pretty nice for somehow association schema of models. That is the concept of model capsules. A model capsule is nothing else as I have a model that has a number of submodels, and these submodels are made for exchange among models in a model suite, and only these submodels can be used for exchange in a model suite. So we have an automatic submodel association for maintained association of models. Let's show it only graphically. You have a model A. The model A represents some kind of setting, some kind of deep model behind. And in this case you say, okay, fine. I can now export from my model A submodel that is understandable and integratable into a submodel of model B. In this case, I have now this kind of tight association. At the same time, of course, B can also somehow export something to A. We can do it for scientific disciplines, we can do it for theories, we can do it for a model suite that represents a number of different facets. In all cases, we have some kind of inner part that doesn't change, only the outer part is somehow consisting of our, let's say, exchange models. And whenever I'm exporting from A to B something, then of course in this case something in B can be changed, but only this part of importing submodel of B must consider this kind of change. This is the same as we have already seen in our, let's say, classical statements. We have a model, we have a mapping to a submodel. That means in extract facility we transform this submodel to a submodel that is somehow possible to have to properly mapped to what our second model could accept. Again, we have maybe some kind of infomorphism mapping, so that we have all model elements also somehow transferred, and then we can say, okay, fine, then we exchange it by mapping or loading into the other submodel. That means it's a model capsule concept is a pretty nice concept in order to have this kind of very nice and tight collaboration among models. Okay, I think it requires now a little bit of a case study. I will make a case study for two cases. One is for information systems development, and another one is for UML development. In both cases we have horizontal model suites. We could extend it to abstraction layered model suites, but I think it is I should show it only how it works. And additionally, I will show you that we have also been developing a number of tools that could support such exchange among models. Let's start with UML. UML consists of a good number of diagram languages. Some of them are representing structures, others are representing behaviors, or third ones are representing interactions. So in this case you might have class diagrams or object diagrams as a language, and you can represent now a number of models for structures. You can use a number of models for behavioral means to represent, and you can have of course also some kind of diagrams for having this kind of component architecture. Michael Skusa has been developing based on a very general ASM backed approach this kind of association. Let's say we have something like we specify a use case diagram, pictured here in this way. The use case diagram of course relates our use case to a name of a package of class diagrams. So in this case you can say, okay fine, in my class diagram I can have a number of attributes, a number of properties represented in this class diagram model. Additionally, I have an interaction model that says, okay fine, for objects with these lifelines you have different, let's say, behaviors, usages of the data in this part. It means in this case we are using now in general 4 different models. One for use cases or business use cases, another one for class diagrams, and another one for somehow our sequence diagrams. If you come now and say, okay fine, oh my goodness, I have to modify something in this case, of course this has an impact in the properties I want to represent for my use cases, and of course it has also an impact on some kind of object diagrams as a sequence or interaction diagrams that represent the behavior. Okay, in this case I have to change it somehow. Then in this case, oh, this is a German version, I say, okay fine, now I have to handle this by a change here in the class model, but I have this kind of consistency constraints I have to consider in my setting here. Since we have been trying to have a general representation language for all these different diagrams based on this abstract state machine approach, then we can say, okay fine, then in this case it is nothing else as we have to handle constraints among these different models in our model suite. Okay, so we say now we go for maybe some kind of change. We have to change here, we have to change it of course for our interaction and sequence diagrams in that way, and then in this case we can say, okay fine, this change is now reflected in such a way that we can resolve this problem in a proper form. How to make it a bit more, let's say, concrete. Let's take a very simple use case diagram. You have something like a use case loan of a book, let's say in a library system. You have a return and you have a borrow. Of course you have books represented somehow. Then in this case you can say, okay fine, in this case I have now somehow related to books a number of additional classes in my diagram. Let's say student, borrowed by student, borrowed by employee, and you have employee. And you might have, let's say, some kind of state chart diagram that says, okay fine, which action follows by which action, and then in this case borrowing means you have to return of course as a book. Then you have now a number maybe of governing constraints. One is whatever is represented in the state chart should be representable by means of the class diagram. That means in this case I have some kind of association among element notions. Then I can say, okay fine, in this case I have now some kind of diagram restriction that says, okay fine, in the state chart the states that I can represent must be somehow represented by some kind of classes states in my class diagram. I can also state it in a different way. I can say, okay fine, it is forbidden to change in the class diagram a state without not modifying it in the state chart. Okay, you can write it in this kind of deontic constraint. You can also say, okay fine, if I have to change something, then I'm obliged to cascade the modification in the class diagram to a modification in the state diagram. And now I come down to my somehow tracer and somehow my controller. My controller says, okay, fine. If an agent 1 comes to modify my class diagram, then my tracer and my controller says, please agent 2 modify your class diagram in a proper form so that it can be handled to have this kind of constraint here. That means in this case we can represent our association and our restrictions to changes by some kind of rules based on the languages that we are using for the model suite. This can be also done for tool support, how it was done in MetaCase. This is a MetaCase slide taken from the PhD of Argenta. We can also do it for modeling websites. You have a specification of a storyboard, in the website. You have a specification of the entity relationship schema that is used and that is representing our data in our website. And you have another diagram that represents, let's say, something like the flow of activities and the flow of function usage. And of course you have maybe a little bit surveying diagram showing you what else you have to use. It comes down that you say, okay, fine, in this case you have now, let's say, something like a live case change. In this case you are using a different layouts of different model languages, the different, let's say, changes. So you say, okay, fine, in this case you have perspectives in the diagram and you have the changes directly displayed in the diagram. That means in this case, if I change here, I will have an impact on all the other diagrams that are shown what has been changed in what way. That means in this case, one trick here in this diagram is that you can use, let's say, some hooks, and then you can pull out some of the diagrams so that you can consider what kind of changes you have been doing. For this reason, for instance, for this part, this diagram in the middle, I'm using now this kind of envisioned diagram for the changes in my live case. A second case, a model suite for information systems development typically consists of my thoughts about an information system as a social system. It consists also on my thoughts or conceptualization on the structure and on the functionality. That is, however, based on my business data process and viewpoint model that comes from my understanding of my information system as a social system. In order to implement it, I'm using now some kind of mapping from the conceptual structures to the logical structures, enhanced, of course, by some kind of functionality model. The same can be also done now for the physical structures, which are now somehow the basis for the implementation. I have now the information system as a technical system. That means in this case I'm working on the same abstraction layer. However, I have now 1, 2, 3, 4, 5, 6, 7 different models in my model suite that I can handle whenever I develop my information system as a technical system based on my thoughts as a social system. This is the origin. This is now the model suite that we're using based on this origin, and I'm using now this model suite to develop another model, maybe also model suite, for my technical realization. The problem in this case is, of course, that some of the models I'm using don't correspond to other models. For instance, I can say, okay, fine, my business data model corresponds very nicely to this kind of conceptual model. Oh my goodness, I have no logical representation for it. For this reason, maybe I should better represent it by another conceptual model that is somehow nicely representable, maybe by this logical data model and this physical data model. I can say, no, my goodness, I have also a different business data model I want to represent as well. For this reason, I have to have of course, this kind of logical models that represents it has a number of opportunities to be represented by physical data models. That means in this case I have now a number of choices. We will come back to it in chapter 14 when we have to map these different models so that we can handle it in a proper form in a holistic setting. Okay, that would be now the story about model suites. Next, I will introduce some kind of supporting mechanism, some kind of easing mechanism, how to develop a model, how to use a model in a proper form, and I will use stereotypes and frames for this development. As a supporting means. So in this case, it means I'm using now in the next chapter stereotypes of models. Models are often not developed from scratch, as we do in greenfield development. They are often brownfield development. Models often have a history we have to consider. We have a treatment according to the level of abstraction, scope of consideration, and the focus of attention. We have also different approaches how we can do it in an integrated form. My proposal here is to have some kind of triple stereotype pattern and template for having a very nice representation of this kind of integration of a model suite in general, for model-driven development especially. And I will also introduce canonic stereotypes for that allow some kind of proper stepwise refinement to the most appropriate model. That is now the whole story that comes in the next lecture. So I thank you. I think now it is time to relax, to enjoy the beautiful life, and to look what comes next in modeling.